Let's look at some pattern types again. So we've looked at a few examples where the patterns were the same distance around, each piece was the same distance apart. And we say that pattern has a common difference. And in the past, I've given that a couple of different titles. Sometimes we call it an arithmetic pattern, which looks like arithmetic, and it is, but when we use it that way, we say arithmetic. Sometimes we call it linear. Example was the one we looked at recently, 2, 5, 8, 11. And we found, if I called this pattern A, that if we take 3 times n minus 1, that tells us how to get the first or second or third or fourth number in the list there. Now, often instead of just an A to indicate we're only doing counting numbers instead of something like y equals mx plus b, often there'll be a little subscript n there. So if I wrote A4, that means n is 4, and I should plug in 4 into the formula. 3 times 4 is 12 minus 1. So this says the fourth term in list A is 11. So you're going to see that notation in the homework occasionally. An alternative way to write that is the way you might have written it in algebra class, something like y equals 3x minus 1. And so here I'm just using an n to say we're just counting. We're not looking at any possible number like 1/2 or 2/3 or pi. We're only looking at counting numbers, right? So n is the position in the list. First number, second number, third number, fourth number. So this just says the fourth number in the list is 11. When we do have that common difference, right, these are all 3 apart in pairs, that's called arithmetic or linear. Another kind of pattern that is common, if I look at the sequence 1, 2, 4, 8, 16, here there isn't a common difference. So if I look at how to get from one to the other, 2 minus 1 is 1, I would add 1. 4 minus 2 is 2, so I would add 2 to make that jump, and then I add 4, and then I add 8. And we can perceive a pattern to the 1, 2, 4, 8. It matches the pattern of 1, which is a little bit weird. So this one right here is not linear. So instead of looking at the common difference, we're going to look at a common ratio instead. So what does that mean? 1 divided by 2 is 2. So instead, what I could say is to get from here to here, we multiply by 2. 4 divided by 2 is 2. So these have a common multiple instead, or a common ratio, times 2 each time. So 16 times 2 is going to give me the next term of 32, times 2 is going to give me 64, and so on. So instead of repeated addition like I had above, now I have repeated multiplication. And hopefully you remember repeated multiplication is an exponent. So let's make a table, try and come up with a formula for this. And sometimes I think horizontally with these patterns, but sometimes it's helpful to think vertically. And you may have a preference one over the other. And for me, it kind of depends on the day and the numbers I'm looking at. So I have my n, we're going to call this sequence B. And the first number is 1, the second number is 2, the third number is 4, the fourth number was 8, the fifth number was 16 that I started with. And again, I noticed that there's this common multiple. So that's important. And another thing that's important is that I started with 1. So this 2 right here came from starting with 1 and multiplying by 2 once. The 4, you could look at it as starting with 1, multiply by 2 times. So starting at 1, multiply by 2 twice. That's where the exponent comes in. To get to the 8 there, starting at 1, we would multiply by 2. 1, 2, 3 times to get to the 8. So that would be 1 times 2 to the 3rd power. And 16, starting at 1, we multiplied by 2. 1, 2, 3, 4 times to get that 16 right there. So things that are changing. The position in the list is changing, and the power is changing, right? Power we use synonymously with exponent. 4, 3, 2, 2 to the first power is 2. And if I think about the sequence 4, 3, 2, 1, the previous number would be 0. Let's see if that makes sense. Is 1 equal to 1 times 2 to the power 0? And I'm thinking back, yeah, I remember that if you raise something to the power 0, you get a 1. So this right here cleans up to be 1 times 1, which is 1. So there's definitely a pattern. And then notice, kind of like a pattern we looked at before, the exponent is 1 less than the position. The exponent is 1 less the position, right? Position 4, exponent 3. Position 5, exponent 4. So I think for the formula, what we call the nth term formula, it would be starting at 1, multiply by 2, and minus 1 times. We'll do another one of those to check. First, we need to check this one. Now, just because I was able to write a formula doesn't mean I did it right. A couple things to think about here. Multiplying by 1 is kind of boring. Nothing happens. So I can clean this up a little bit and just say it's 2 to the power and minus 1. And so next I need to check the formula. So I'm going to scoot over here to this empty space. And let's go in red. This is the first term. That's the second. That's the third. That's the fourth. Let's check our formula, see if it works. So my claim is that the fourth value of B in that sequence, this is sequence B here, is going to be 2 to the power 4 minus 1. Order of operations, we got to do that 4 minus 1 first. That's 2 to the 3rd power, which is 2 times 2 times 2 on a good day, 8. And yeah, that checks. I was hoping to get an 8 there. Okay, just in case I'm having a bad day, I should check again. So let's check it for the 5th number. I expect to get 16. So the 5th number in the list, B with a little subscript 5, would be 2 to the power 5 minus 1, which is 2 to the 4th, which is 4 2's multiplied. 4 times 4 is 16. Double check on a calculator if we need to, and that is what I was hoping to see. So my formula is checking out here. When we have this common ratio, this common multiple here, this type of sequence is called either geometric or exponential. So we have a couple of sequences with names. We have our arithmetic or linear list of numbers pattern, and we have our exponential or geometric pattern. Last class, I mentioned a couple of other ones, which I'm not as interested in developing formulas on because we could do this forever, and that's really not what this class is about. It's just, there are lots of patterns. We can describe patterns with tables and graphs and formulas. So a couple that we came across last time were the Fibonacci numbers, Fibonacci lists, Fibonacci sequences. Fibonacci is where we add the previous 2 terms to get the next one. The book has a story about reproducing bunnies that you should read for this. Previous 2 terms to get next term. You can start with any 2 numbers you want. Typically, we start off with 1 and 1. 1 plus 1 is 2. And then 1 plus 2 is 3. 2 plus 3 would be 5. 3 plus 5 would be 8. and so on. Now, this one, there is not an easy formula that you can just plug n into. I can write an equation, so I can take this statement right here and I can put it in mathematical terms. And I'll do it in the following way. So I'm going to use that subscript notation that I used over here. So let's call this sequence F for Fibonacci. So if somebody says, hey, what is F3? I would look at the list and go 1, 2, 3, that would be the number 2. What is F4? What's the fourth number in the list? 1, 2, 3, 4. It would be 3. What's F5? And that's a little subscripted 5 there. 1, 2, 3, 4. Oh, it happens to be 5. What's F6? Well, it happens to be 8. Now, I'm going to kind of skip down here. What I'd like is to have a formula where I can just kind of plug in n. And I mentioned earlier, there really isn't an easy one, but I'm going to give you one that translates this statement right there. So where did that 8 come from? The 8 came from the 5 plus the 3, or the 3 plus the 5, however you want to add those. Where'd the 5 come from? The 5 came from the 2 plus the 3. Where'd the 3 come from? It came from the 2 plus the 1. And that 2 came from the first two 1s added up. Now, let's focus on, let's say, row F5 here. The 2, right, that's the third number in the list. So another way I could write this is I took the second number and I added, no, I took the third number, right, 2 is 1, 2, third number, and I added the fourth number, right? To get the fifth number, I take the third number and add it to the fourth number. Isn't that what this says right here? Add the 2 previous terms to get the next one. Let's think about that. For the 6th term, the term before the 6th one should be the 4th and the 5th. So if I take the 4th term, add it to the 5th term, that should give me the 6th term. So 3 is the 4th term and 5 is the 5th term, and yep, that's how I got the 8. Hang on one second. All right. So in general, how can I describe this? Well, remember before we talked about the previous number. So if I'm at n, the previous number is n minus 1. So here, if I'm at n, like 6, the previous number is 5. So that second number is the n minus 1 term. That would be the one right before, 1 before n. Now, if I'm at 6 and I want the fourth number, that would be 2 numbers before. So we would write that by saying n minus 2. So this is one way to write a formula. This is the mathematical way to say, add the previous 2 terms. That's supposed to be an arrow. Now that formula is only useful if I tell you where to start. So I would say, I would add to this where F1 equals 1 and F2 equals 1. So this here tells you where to start, and this tells you how to continue that sequence there. So if somebody wants the 100th term, well, they're going to have to know the 99th and the 98th, which means they need the 98th and the 97th. So with this formula, there is no other way to do it by just to go through this way, one way at a time. You just got to jump one number at a time and keep adding them up. Is there a formula where you can just plug in n? Yes, there is. It's very complicated to come up with, and it's very complicated to use. This is way easier, right? That gets me the answer. And we can start anywhere we want. We don't have to start at 1 and 1. All right. Other kind of pattern I talked about last time were called quadratic. And quadratic patterns came up in a couple of different ways. One way is they had a common second difference. So let's take list, let's call this list C. I haven't done a C yet. And the numbers are going to be 1, 4, 9, 16, and 25. And if we look for a common difference here, to get from 1 to 4, the difference is +3. 4 to 9, the difference is +5. To get from 9 to 16, that's a +7. And to get from 16 to 25, that's a +9. Notice we don't have a common first difference like we did with some other ones. However, I do notice that, hey, wait, 3 and 5 and 5 and 7, they're the same distance apart. So now I'm going to do a second set of differences. 3 to 5 is a difference of 2. 5 to 7 is a difference of 2. That's a difference of 2, right? So I have a common second difference, not a common first difference. And when you have that kind of situation, you get what's called quadratic. Quadratic, quad means square. So that means the formula with n is going to have an n squared in it. Now it turns out that's actually the formula here. It's not always that easy, but if you notice, 1 is the first term, 2 is the second, 4 is the second, 9 is the third, 16 is the fourth, 25 is the fifth. And 5 squared is 25, 4 squared is 16, 3 squared is 9, 2 squared is 4. Tons of other quadratic patterns out there. This is just one of them. They all have this property that the second difference will be fixed. Now, it's not always going to be 2. It could be 1. It could be 3. Okay, it could be any number out there. But if the second distance difference is common, that means you're going to see a square as the highest power. Oops. Power has a P, not a B. Highest power is 2. So quadratic refers to the square. The highest power is 2 in the formula. So what kinds of sequences do we have so far? We've got those linear ones. We've got the geometric ones. We've got the Fibonacci ones. Now we get the quadratics, and there's a ton of others. Some of them have names and some of them don't. We're just going to leave it at that. And most of the homework is playing around with these kinds of sequences, trying to continue them, trying to come up with a formula some of the time, but not all the time.